All right.
All right, can you hear?
Yeah.
All right, we're recording.
Good evening.
Hello.
I mean,
Oh, you start. You start.
okay, sorry. Hello guys. So let me shut my window. Sorry. It's really loud. All right. Sorry. Okay. This is our noise cancellation hearing aid senior project. My name is Dennis Bly.
My name is Josiah Donegan. Yeah, let's start. But yeah.
This is our agenda. We're just going to pretty much just go over the problem statement, the purpose, the audience, the relevant courses, and then we're going to go down all the way from the theory, like background information. Then we're going to explain the components, and then the industry standards, the methods, and then the data and the results.
So, so what's the problem? Over 1.5 billion people worldwide experience some degree of hearing loss, and they often struggle to distinguish human speech from background noise in everyday environments. Typical hearing aids amplify all sound, which is sort of counterintuitive, and that can overwhelm the listener who's trying to just hear human, who's just trying to distinguish the human speech clarity. So to address this challenge, we present a hearing aid attachment that uses decibel level monitoring and beam forming signal processing to reduce the unwanted background noise while amplifying human speech, and for hopefully an affordable price.
The purpose of this project is to improve communication to those who can't really hear as well, provide comfort, being out in public spaces. You want to be able to feel comfortable with having your hearing device in versus everything being amplified all at once. Increase the quality of life for hearing aid users, and just provide opportunities to individuals who may not afford the expensive hearing aids that are ranging in the thousands.
Mhm. So our main scope for the audience is the elderly individuals with mild to moderate hearing loss, people with people who want low cost hearing aids, individuals that are sensitive to noisy environments, uh, potentially audiologists and nursing homes. And the smaller scope could would be students or workers with hearing impairments and community health programs. The relevant uh, courses necessary for to accomplish this goal was communication as engineering, signals and systems, electronic devices, control systems, and microcontrollers. So the theory and science. The the theories we're going to be using is microphone array processing, beam forming, which is sum and difference. We're doing using one-dimensional beam forming, time delay on arrival, noise suppression using spatial filtering, I2S digital microphones with ESP32 processing, and we'll explain that later. The science behind our product comes from the microphone array beamforming. So when two microphones are spaced apart, uh, a sound reaches a sound can reach from the front, while a sound can reach from the front and it reaches both mics at the same time, while a sound from the side reaches one mic earlier and can be louder to one mic at a time, while it's less for the other. By adding or subtracting the microphone signals, we can emphasize speech coming directly from ahead or coming from the sides or off axis.
Um,
So
some
what do you think?
background information that we can both cover is a signal is basically anything or any function that carries or represents data or energy. So most intelligible speech lies between 250 hertz and 6 kilohertz. The latency is the time delay for the audio input to output, ranging up to around 10 milliseconds. The higher latency and the more echoey it gets. Beamforming is a method that we're considering using. It is a processing technique that uses two or more mics to focus on sound from a particular direction while reducing sounds from many different directions.
All right. So now we're in the component section. Our first and most important component will be the Arduino ESP32 with the I2S interface, audio sampling rate of 48 kilohertz, operating voltage or 3.0 to 3.6 volts. Can use Wi-Fi 2.4 gigahertz, the BLE 5.0 to BT mesh, and it's very small. It's about this big right here, and it uses USB 2.0.
Yeah.
This is where most of the processing, or this is where all of the processing for our project is going to happen. This is where the noise canceling and all that.
We're going to be also using two MEMS microphones, the Adafruit I2S SPH0645LM4H, and then some power pins that are going to be used. The 3 volts power pin, it ranges from 1.6 volts to 3.6 volts. The ground will be, for the power and the data ground, and then the I2S data pins, which are going to be the big clock, usually around 2 to 4 megahertz, and the data output for the mic. And then the left right clock is when the low left side will transmit, and then when the high right side will transmit. And then the LCN is of course the select pin, the channel select pin.
And the purpose of the mics is to, of course, capture all the audio and bring it to the ESP32 processing.
Yeah.
So now these are components we have to implement next semester. The Adafruit Max 98357A, the I2S 3-watt Class D amplifier breakout with the voltage range of 3.3 volts to 5. This will, when all the processing is said and done for uh for what the mics bring in and process through the ESP32, before it gets to the earbuds, it's going to go through the amplifier. This will increase the intensity of the sound that we want. And after all the processing has happened, it's only going to amplify the desired sounds.
And this is the earbud receivers that are going to be coming from the amplifier, so that the user can actually hear the noise cancellation through their environment. And then the impedance, of course, is 16 ohms.
And of course, we want to make this portable. We want to make this device portable and last a long time. So we are implementing the 3.7 volt lithium ion battery. It's light at 23 grams, dimensions 34 by 62 by 5 millimeters. And the output is 1200 milli
Milliamp hours.
milliamp hours at 3.7 volts.
And then this is our buck converter, or step up or step down voltage regulator. Um, this is the Pololu. The dimensions are 45 by 16 by 0.1, and the weight is 0.6 grams. The max voltage is 11.8 volts, and then the minimum is 2.7 volts, and the output is 3.3 volts. So this is compatible for our design. We're trying to make sure it steps down to 3.3 volts when we apply the 3.7 lithium ion battery pack.
Yes, and this is of course essential for our design because this is going to protect our system from from the lithium ion battery because otherwise it would possibly fry the system if we
Yeah.
don't step it down.
These are some of our
Mm,
parameters. The acoustic input level ranges around 30 to 90 decibels. Um, the voice priority band, like we stated earlier, is around 250 hertz to 6 kilohertz. And then, of course, our battery, we need our battery, which is a 3.7 volt lithium ion 12 milliamp hour battery with a 3.3 buck or boost regulator for the stable rails. The signal to noise ratio improvement would be less than or equal up to around 10 decibels for speech enhancing.
yes.
But we still have to go back and make sure that's accurate and everything.
Yes, we could possibly go lower than 10
Yeah.
decibels if possible.
Yeah. And then the form
Um,
factor that we're trying to do like a waist clip on, or another method we could do is like a chest clip on, as stated when we presented last time, when we talked about how we can implement either like some type of chest or waist, but we're more so leaning towards the waist. I mean, yeah,
And the latency, we want it to be less than 10 milliseconds. Latency is of course, the time delay from audio input to output.
yeah.
The higher, the more echo distortion.
And then some industry health standards that I saw that would be for our design, a max output level. Um, you want it to be around 110 decibels. You really don't want much more than that. And then the safe gain limits is between 20 to 25 decibels. And then they also stated that the frequency range, of course, should be from 250 hertz to 6 kilohertz. And the latency could be 20 milliseconds or less. Um, the internal operating temperature, they said it can't be no more than 140 degrees Fahrenheit, or it can be like at least around that's around the operating temperature should be.
Mhm,
Of course, we should definitely avoid excessive moisture that could possibly damage the components within the system. No sharp edges, so because you don't want anything poking anybody or any body part from the device. And then
mhm,
definitely allow proper venting to the system so the system doesn't overheat. And then no soldering pads near bare skin, because I could definitely cut someone and damage a body part on someone that are using the device.
mhm. So just
I
to
mean,
reiterate, our method is to use the two I2S MEMS microphones capturing the surrounding audio. The microphone spacing enables the directional pickup and basic noise reduction. Signals are read at 16 kilohertz at a 16 kilohertz sampling rate for speech clarity. The beamforming, we'll implement the beamforming and the amplifier to drive the speaker bud. And of course, like we said, we'll do the waist clip-on design. We'll test with the waist clip-on design. Now, this is a basic flow chart of how just to reiterate the design and the processing procedure. So it captures the audio from the MEMS microphones, then applies the bandpass filter, then applies the gain and limiter. That'll happen within the code. The code will do that part. Send it to the amplifier, and once it amplifies, does its job, it'll send the output to the earbud, and then you'll hear the results at that point.
this is our system level diagram. It is a little bit more complex just to show like what's being inputted, processed, and what the audio output is and how the power is, well, how the system is going to gain its power. So the input will be the two I2S MEMS microphones. And then the processing stage would be the filtering, the gain, the limiter, and then of course the noise reduction. And then that will go all hand in hand into the audio output, which would be the amplifier, and then that will go into the earbud receiver. So that way, of course, the user can actually hear the noises in the back. Well, hear the noises being picked up from the mics better. And then that'll all be powered through the 3.7 lithium ion battery and the 3.3 voltage step down regulator to make sure we don't have overpowering of the system.
Hmm. So the sum versus the difference, noise suppression. This is where the math happens. This is where the magic happens. So the sum beam, we use the sum and difference beams, we use these formulas to determine the directional beams. And the directional beams determine what's getting enhanced and what's getting canceled out. The sum enhances the sum beam enhances sounds coming from the front, and the difference beam enhances sounds coming from the side. So just to explain the mathematics, it would be the left RMS plus the right RMS divided by 2. That would give us our sum beam. And for the difference beam, that would be left RMS minus the right RMS divided by 2. And that would give us our difference beam.
And this is
This is
just
the Arduino. This is just the Arduino code.
yeah.
So just for reference, this is mostly where the math happens. This is the part where the math would happen in the code. Our progress so far this semester, we've gotten the stereo RMS to successfully capture from both mics. The quiet RMS baseline is around 0 to 1, and it drops lower with DC removal. The quiet RMS is just when no noise is being is we're not trying to apply any noise to either mic, so it remains at a base level value. Um, we cleared RMS spikes. We're clear on RMS spikes when speaking or clapping near one mic. The sum signal is stronger for forward sounds. The difference signal is stronger for side sounds. All of this is working so far. And we also verified the I2S signals on the Keysight oscilloscope.
Yeah. And this is just the data showing from the mics being picked up. It shows the left and the right mics, and then the sum and the differences.
So yes, we'll have left RMS here, right RMS here. This is, yeah, of course, quiet RMS. It's around zero point 0.1. This is when it's quiet. We're not applying anything. So of course the difference is going to be low, little to nothing. The left RMS, this is one, you see it's significantly spiked. Right RMS hasn't seen much of a difference. And for the right RMS shift, we see the right RMS is receiving more sound and it's spiking more than the left RMS. And as a result, the sums and differences are way more different between both.
Yeah.
So the data, oh, you want to go?
Oh, it doesn't matter. I would say the sample. Well, from the sample one, the left mic was measuring much higher amplitudes compared to the right mic, and that just shows that the it has strong spatial separations. And then for sample two, it just shows that the mic displays higher amplitude, which confirms that the sound source was coming stronger from the right side, being that the right values were higher. And
Hmm.
then for sample three, it's basically showing that the left and right values are nearly identical, and that can be shown through the difference values, which they're showing little to none changes. So that's why the numbers are much smaller.
Hmm. All right, we're almost done. So the possible constraint is the sizing of our components. Most of the components we have so far are in line with what the size we want to have for our device so far. We just need to make sure any of our future components we organize them properly because none of them look to be too big.
Yeah,
So I think we'll so I think we'll be in terms of sizing, we should be we should be able to make this work. The battery life due to the small structure, that's a variable we have to figure out. We have to make sure we want to make sure the it can at least last at least 4 hours starting off, 4 to 6 hours starting off on a single charge. And the durability due to sweat and moisture, this is a huge problem. This affects wear and tear of any device. Of course, we don't want our device breaking down within the first year of use
yeah.
due to due to these factors, due to just daily use and sweat and moisture. We want it to be immune to that stuff, or almost. And the placement of the device for noise cancellation. Like we said, we're doing the waist clip-on method. So the noise cancellation, we're trying to figure out where we want the audio to be captured. But in terms of the noise cancellation, the processing is going to happen certainly at the waist.
Yeah.
But as for the capturing of the sound, we'll think on how that will work. And our future plans. Our next step in development will be to implement devices such as the amplifier, like we said, which will help increase the intensity of the desired sounds. The Skull Candy earbuds will be used to test the device, and the voltage regulators will be implemented to protect the system when the rechargeable lithium battery is used to power it. And like we said, the waist clip-on design will be will be for our final prototype, likely.
What
And
did we learn in EEN-498? I would say for this project, we definitely learned about hardware details, getting the specifications for the components, the GPIO mapping for like the ESP32 and groundings for them, and how they directly affect microphone performances. We also gained experience using the I2S digital audio. This is our first time using the MEMS mics. Um, so we're going to incorporate them into our system. And for the beamforming methods, definitely beamforming math. That's something that we're also learning with this technique that we're using. And then we definitely learned like how important it is like on the ethical levels with designing your devices and making sure you're not taking shortcuts to make sure these devices are actually being able to perform and not harm users, and just making sure we're keeping people in mind and our loved ones in mind when we're creating these devices.
mhm.
And these are
These are
just,
our references.
yeah.
Is all we learned. Thank you very much,
Thank you
and
guys.
we'll see you next semester.
Thank you, Dr. Mead.
Thank you, Dr. Maid.
We did it. And I was
Yeah.
it was over 22 minutes.